Hello everyone, welcome back to the online session on dynamics of machines. In previous session, we have learnt about the derivation of differential equation of damped free vibration and the conditions based on damping factor, that is over damping, critical damping and under damping system. And also we have derived one more derivation, that is logarithmic decrement. Now in today's session, we are going to solve some numerical problems based on the damped free vibration. Now let us see the first problem. Problem number 1. A spring mass damper system is shown in the figure. So it is the given figure, spring mass damper system, K 70,000 Newton per meter and C damping coefficient C, that is 700 Newton second per meter. Unit of damping coefficient is Newton second per meter. So the given damping coefficient is 700 Newton second per meter and the mass is 175 kg. It is given in the question itself, and they are asking to find natural frequency of undamped vibration, and also if you find the omega n, you can find out the frequency, natural frequency in hertz. Then damping factor means zeta, natural frequency of damped vibration. So we have to find out the natural frequency of damped vibration as well as undamped vibration, and logarithmic decrement. So this is the given question. Now we will find the first factor, natural frequency of undamped vibration. So to find out the natural frequency of undamped vibration, the formula is Fn is equal to 1 by 2 pi into omega n into omega n. So that we will express it in hertz, 1 by 2 pi into omega n. Now we have to find out omega n. So we know the formula, omega n is equal to square root of k by m. We know the value of k also, it is given in the question itself, 70,000 Newton per meter by the mass 175 kg. So if you simplify this, you will get 20 radian per second, 20 radian per second. Now substitute this 20 in place of omega n, so we will get natural frequency as 3.183 hertz, 3.183 hertz. Now we got the value of natural frequency of undamped vibration. Now second one, damping factor means zeta. What is the formula to find out damping factor? C by Cc. C by Cc. C, damping coefficient, that is C, given in the problem only, 700 Newton second per meter, and Cc, critical damping coefficient, that we don't know, that we have to find out. For that we have a formula 2m into omega n. Cc is equal to 2m into omega n. So 2 into m is 175 into omega n is how much? 20. So 2 into 175 into 20 will get 7000 Newton second per meter. 7000 Newton second per meter. So this is what Cc, critical damping coefficient. For that we have a formula 2m into omega n. Damping coefficient C, that is given in the problem itself, that is 700 Newton second per meter. What we got, 7000 Newton second per meter is critical damping coefficient. Now as per the formula, damping factor zeta is equal to 700 by 7000 is equal to, we will get 0.1. So zeta value is 0.1. So now next one is natural frequency of damped vibration. Here we got natural frequency of undamped vibration. Here we need to find out natural frequency of damped vibration, means Fd, natural frequency of the damped vibration, that is equal to 1 by 2 pi into omega d. Here we have taken the omega n because it is the undamped vibration. Here we are considering omega d since it is the damped natural frequency. So for omega d we know the formula omega n into square root of 1 minus zeta square. So for that we got the damped circular frequency or angular frequency of damped vibration, that is 19.9 radian per second. Because we know the value of omega n 20 and zeta value 0.1. So if you simplify, you will get 19.9 radian per second. Now put this 19.9 in place of omega d. So you will get natural frequency of damped vibration, that is 3.167 hertz. 3.167 hertz. Here for the undamped natural frequency we got 3.183 hertz. Now last one, logarithmic decrement. We know the formula, delta is equal to 2 pi zeta divided by square root of 1 minus zeta square. 2 pi zeta divided by square root of 1 minus zeta square. We got the value of zeta, how much? 0.1. Now substitute in place of zeta, so we will get delta, that is logarithmic decrement, as 0.6315. 0.6315. So this is about our first problem. It is like a direct question. They have given the values K, M and C in figure itself. So now we have got the values of natural frequency of undamped vibration and natural frequency of damped vibration. Along with that, we got the value of damping factor and logarithmic decrement. So this is about our first problem. Now we will see one more problem. Problem number 2. A spring mass damper system has, means like this system only, spring mass damper system, has mass 3 kg, and K is 100 Newton per meter and C 3 Newton second per meter. I will repeat once again, mass M is 3 kg, K is equal to 100 Newton per meter, C damping coefficient is equal to 3 Newton second per meter. Determine first one, damping factor, natural frequency of damped vibration, the ratio of two successive amplitudes, number of cycles after which the original amplitude is below 20%. Below 20%. Same thing, they have given mass value, K value and the C value. They are asking to find damping factor first. So we know the value, we know the formula for damping factor or damping ratio, that is zeta is equal to C by Cc. For C it is given 3 Newton second per meter, it is in the question itself. We need to find out Cc. For that we know the formula 2m into omega n. 2 into 3 into omega n is what? Square root of k by m. If you do square root of k by m, you will get 5.773 radian per second of your omega n value. Then put this value in place of omega n to find out Cc. So you will get Cc as 34.641 Newton second per meter. Newton second per meter. Now you can find out the value of damping factor. So 3 is C, 34.64 is Cc. So we will get damping factor as 0.0866. 0.0866. Then second, natural frequency of damped vibration means Fd. To find Fd, first we need to find out omega d, right? So the formula to calculate omega d is what? Square root of 1 minus zeta square into omega n, or omega n into square root of 1 minus zeta square. So we got the value of omega d as 5.7518 radian per second. How we got this value? By considering the formula square root of 1 minus zeta square into omega n. Omega n we know, we got the omega n value as 5.773 radian per second, and zeta 0.0866, just substitute here. So we will get omega d as 5.7518 radian per second. Now natural frequency of damped vibration. So Fd is equal to 1 by 2 pi into omega d. 1 by 2 pi into, in place of omega d we have the value 5.7518. So we will get Fd is equal to 0.9154 hertz. Frequency, natural frequency of damped vibration. Now, third one. This is third one, the ratio of two successive amplitudes. The ratio of two successive amplitudes. So for that, we know the condition, that is xn by xn plus 1 is equal to e power delta. That is what the definition of the logarithmic decrement. What it says, the ratio of two successive amplitudes under underdamped system on the same side. So for that we have the condition xn by xn plus 1 means x0 by x1 or x1 by x2, like that. So for that, in general, xn by xn plus 1 is equal to e power delta. But we don't know the value of delta, means logarithmic decrement, that we need to find out. So to find out logarithmic decrement, we know the formula, delta is equal to 2 pi zeta divided by square root of 1 minus zeta square. We know the value of zeta, substitute the value of zeta here, so we'll get delta logarithmic decrement as 0.5462. 0.5462. Now use this delta value here in place of delta. So xn by xn plus 1, that is ratio of two successive amplitudes, is 1.7226. 1.7226. Now the fourth question, number of cycles after which the original amplitude is below 20%. Underline this, below 20%. Means while deriving the logarithmic decrement, we know that for a logarithmic decrement we have a formula, delta is equal to 2 pi zeta by square root of 1 minus zeta square. But when we consider the more number of cycles, we have one more condition, that is delta is equal to 1 by n natural logarithm ln of x naught by xn. This is the condition for more number of cycles. And here we know the value of delta, that is how much, 0.5462. N that we don't know, that we have to find out number of cycles. X naught by x1, it is clearly given that number of cycles after which the original amplitude is below 20%. So it will become x naught by 0.2 into x naught. Now simplify this, so we'll get n value 2.9466. Approximately it will become 3. So the number of cycles are 3 cycles. Number of cycles are 3 cycles. So this is about the second problem. See, the problem statement itself is saying that it's a spring mass damper system, and in the question itself you will get C value, that is damping coefficient, mass value, and also the K value. The thing is, you need to remember the formulas for each step. You have to remember the condition for each step. So, and while simplifying in your calculator, it is very, very important, because while calculating the answer, we'll miss 1 or 2 digits. So in that condition we may not get the correct answer. So while calculating in each step, be careful. Now we will see the third problem. A spring mass damper system makes 10 damped oscillations per second. I'll read it once again. A spring mass damper system makes 10 damped oscillations per second. Its amplitude reduces to 10% of initial value in 50 cycles. Its amplitude reduces to 10% of its initial value in 50 cycles. Determine damped frequency, logarithmic decrement, and damping factor. See this problem. In the previous problem, you have the value of mass, K values, stiffness of spring, and the damping coefficient. But here you don't have mass, stiffness or any other required parameter to find out the answer. So this problem is quite different from your previous problem. As per the problem statement, spring mass damper system, the system is spring mass damper system and it makes 10 damped oscillations per second. 10 oscillations per second, and its amplitude reduces to 10% of its amplitude in 50 cycles. So to find out damped free frequency, we know the formula, that is what? Omega d by 2 pi. But here they are given in terms of wordings. But as per the problem statement, 10 by 1 means 10 damped oscillations per second will give damped frequency, that is 10 hertz. 10 hertz. Then next, logarithmic decrement. The formula is 2 pi zeta by square root of 1 minus zeta square. But here we don't know the value of zeta, or they have not mentioned in the problem also. But we know one more condition for the logarithmic decrement, that is delta is equal to 1 by n into ln of x naught by xn. Because they are given the number of cycles, how much? 50 cycles. So in place of n we can write 50, and x naught by xn, two successive amplitudes, initial and final, that is how much? X naught by, it is reduces to, and means final amplitude is reduces to 10% of its initial value in 50 cycles, means it will become 1 by 0.1 of x naught of its initial value. So 1 by 50 into ln of x naught by 0.1 x naught. So if you simplify this, you will get logarithmic decrement delta as 0.04605. 0.04605. See, I have just used the statement given in the problem. 10 damped oscillations per second. So the frequency is what? 10 by 1, 10 damped oscillation per second 1. So we will get 10 hertz. Then number of cycles n, 50. And the final amplitude will reduce us to 10% of the initial value in 50 cycles. So x naught by 0.1 by x naught. So we got the logarithmic decrement value as 0.04605. Now last one, damping factor. Damping factor means what? Zeta is equal to C by Cc. But here we don't know the value of C or Cc. But we know the formula, that is delta is equal to 2 pi zeta by square root of 1 minus zeta square, right? So for this formula, delta is equal to 2 pi zeta by square root of 1 minus zeta square. Here we know the value of delta, 2 pi is a constant term, zeta value that we have to find out. So now what we will do, we will do squaring on both sides. So we will get delta square is equal to 4 pi square zeta square divided by 1 minus zeta square. In next step, further simplification, 1 minus zeta square is equal to 4 pi square zeta square divided by delta square. So in the last form we get zeta square is equal to delta square by 4 pi square plus delta square. If you just simplify this formula in terms of zeta, this formula is for logarithmic decrement. Delta is equal to 2 pi zeta by square root of 1 minus zeta square. But what I want is zeta. So just simplify this formula in terms of zeta. So we'll get delta square divided by 4 pi square plus delta square. So just apply the value of delta here. So we'll get zeta is equal to 7.329 into 10 to the power of minus 3 as damping factor. So in this type of problem, when they have not given any mass or damping coefficient value, we can use the hint given in the problem. So based on that we can also find out the damping factor value and as well as the logarithmic decrement value. So this is about third problem. Now we will see the fourth problem. The measurement on a mechanical vibrating system. The measurement on a mechanical vibrating system shows that the spring can be combined to give an equal spring stiffness 5 Newton per millimeter. 5 Newton per millimeter if the vibrating system have a dashpot attached to which exerts a force of 40 Newton. Which exerts a force of 40 Newton when the mass have a unit velocity. When the mass have a unit velocity of 1 meter per second. Determine Cc, critical damping coefficient, zeta, damping factor, delta, logarithmic decrement, xn by xn plus 1 means ratio of two successive amplitudes. Here also we have to find out the same thing, means damping factor, delta, critical damping coefficient, ratio of two successive amplitudes. But see the data given in the problem. The spring stiffness is given K 5 Newton per millimeter. It is in millimeter. 5 Newton per millimeter converted to meter. So you will get 5000 Newton per meter because it is given in Newton per millimeter. When you are going to convert it to meter, you will get 5000 Newton per meter. And if the vibrating system have a dashpot attached which exerts a force of 40 Newton, means the vibrating system has a dashpot, it is exerting a force of 40 Newton. Go back to your different types of damping system. So in the very first type of damping system, viscous damping system, there we have learnt a formula, that is F is equal to C into x dot. F is equal to C into x dot. So here they have given the force, that is how much? 40 Newton, and C damping coefficient, that we don't know, we have to find out, and x dot means what? Velocity. Velocity is given here 40 Newton when the mass have a unit velocity of 1 meter per second, means your x dot is how much? 1. So just simplify this, we will get damping coefficient C is equal to 40 Newton second per meter. 40 Newton second per meter. See, from this data, exerting force and by considering velocity, we got the damping coefficient value. Now to find out Cc, we have one more formula. Cc is equal to 2m into omega n. So omega n square root of k by m, k value 5000, it is given in the problem only. M value 10 kg, it is also given in problem where it is the measurement on mechanical vibrating system shows that 10 kg. Here it is missing, shows that mass of 10 kg. So it is also given in the problem. The measurement on a mechanical vibrating system shows that and a mass of 10 kg, the spring can be combined to give an equal stiffness of 5 Newton millimeter. So 5 Newton per millimeter. So we got the value of C, and here the k by omega n is equal to k by m, 5000 by 10 will get 22.36 radian per second. So that is what the omega n value. Now we have to find out critical damping coefficient. Critical damping coefficient Cc is equal to 2 into 10 into 22.36. So Cc is equal to 447.2 Newton second per meter. Cc will get 447.2 Newton second per meter. So this is how we are going to calculate the critical damping coefficient. Now we will see the damping factor. Zeta is equal to C by Cc. Now we know the value of C, we know the value of Cc, just apply here. So we will get damping factor value as 0.00894 as damping factor. Next we have to find out delta, logarithmic decrement. We know the formula, delta is equal to 2 pi zeta by square root of 1 minus zeta square. So delta is equal to 2 pi into 0.0894 divided by square root of 1 minus 0.0894 whole square, sorry 894 square. So if you simplify this, we will get delta value as 0.564. Now the last one, ratio of two successive amplitudes. For that the condition is xn by xn plus 1 is equal to e power delta. In place of delta, use this value 0.564. So we will get the ratio of two successive amplitudes as 1.758. So this is how we are going to calculate the damping factor, critical damping coefficient, or the ratio of two successive amplitudes, or the number of cycles. So based on this, you will get a problem on damped free vibration in your VTO exam. They may ask to find determine the damping ratio, damping factor, or natural frequency. So they will ask so many parameters based on the different marks. So this is the steps, or this is the procedure how you have to solve it. If you remember the formula, you can solve easily. If you miss any formula, means you will get a wrong answer. So focus on the formula. So in this type of problems, the important thing is you have to remember the formulas. If your formula is wrong, then you will get a wrong answer. So list out the formulas and go through that, so that you will remember and you can solve the problem.